Homework 34, page 335, chapter 7, section 7, numbers 1 through 15 odd. Now be very careful here, because 1 through 5, 11, and 13, I even wrote this on the board. Do what I say. We're going to have 4 things that you will need to do for each one of these. I'll write this all up on the board. We will do examples or at least one example like this for the 4 things that I'm looking for that I want to see on your paper. We'll go over that. Please do what I say, okay? And then for numbers 7 and 9, we'll talk about what they're asking for. I'm going to do a demonstration on Desmos and show you, basically teach you what the book tells you. I'm going to give you a bit more because there's more there. And ultimately, all you're going to do is use Wolfram Alpha. But then I'm going to have, again, do what I say. I'm going to have specific instructions for what I want to see on your paper with these questions. So let's get into it. The topic for today is mathematical models. And a mathematical model is an abstract description of a concrete system using mathematical concepts in a language. We are right now in our class, we're going to be using linear models. And that means there's going to be some phenomenon or something that we could use a line to describe. We'll do that in just a second, but there's 2 very important points I want to make about any mathematical model, not just linear models, any mathematical model. They're almost never 100% accurate. I know this looks weird. They are almost never. What is that? Okay, so there are specific cases, and in fact, the first one from the book that we're going to do is going to be one that is 100% accurate, but that's kind of a fluke. It's not what we do there is not so much a model as more it just comes from a definition of what something is, and that happens to be a linear relationship. This will make more sense in a minute. But let's do an example to show you what I mean by never 100% accurate. Let's imagine that you're in your car and you have cruise control on. So it's keeping the speed at 1 speed, whatever you've selected. And you look out the window, and exactly at 1 o'clock, you see that you're passing mile marker 100. You know what mile markers are. If you look on the highway, like on the side of like every mile or so, it'll have how many miles it's been for, whatever. Usually if you're going on I-5 from south where Washington starts, that's mile marker 1 or 1 mile from the very south of Washington. As you go north on I-5, there's a mile marker every 1 mile. And so imagine you're going north on the highway, and at 1 o'clock, let's say p.m., you notice that you're at mile marker 100. So that means if here's the state of Washington, and you start on I-5 here, 100 miles north, right there, is mile marker 100. So you notice that at 1 p.m., you're at mile marker 100. Then you also, and remember, you have cruise control on, so you're going the same speed. And then you look at 3 p.m., you've been cruising the whole time, and you notice that you are at mile marker 220. Well, we can build a mathematical model of how far we've traveled, where we were, something that will capture all of that. And what I'm going to do is start by saying, hold up, okay, so we have time and miles. So what I'm going to do is I'm going to define some variables. I'm going to say let t equal the time. How about after noon on the day in question in hours? Okay, so every time t moves over 1, you've gone 1 hour. You could do seconds, you could do minutes. I don't want to do that. We're going to say let t be time after noon in hours. So that means that this time must be t equals 1. Now I could have said let noon be 1 or time after 3 a.m. or something like that, but as you can see, this is going to make a lot more sense to just do it this way. That way, at 1, t equals 1. And at 3, then t would have to equal, well, I guess 3. See how nice and easy that is? Now I'm also going to say, let's let d equal distance in miles. I usually put little parentheses around the actual units. Distance in miles. Or we shouldn't actually say distance, it should be position. We'll get way into that later on, probably Algebra 2, I'll be a real stickler about that. But right now, we're just saying this is your position. In fact, let's change it to P. Let's let P equal position. Position in miles on highway. Okay, so I've defined my variables. Now let's plot a couple points here. So let's see where we were. And what I'm going to do is, and you usually, whenever you're dealing with time is you put on the input axis. This is also called your dependent variable. And then the other thing, we'll just say, is what we're going to put on our other axis there, right? Usually the thing that's just clicking along, like time, you can't change time, it's just going to keep stepping forward. That's the thing that you put right here. And then you have some kind of phenomenon that depends on the time, and that's the thing you put right here. Don't worry, don't try to get too big of a hold on that, especially because in this homework, they're going to tell you explicitly which one to put where, okay? And it actually, in this case, with a linear model, it won't matter whether you do it the other way, but they're going to, it takes some getting used to, and after you've done about 1,000 of these, you'll have a good feel for what goes where. But for right now, and as a rule of thumb, time is almost always that one. Okay, so let's plot a couple points. We know that when time equals 1, our position is 100. You could think about this as a point where you have time, position, like that. In this case, then, and notice that this determines which axis is which, right? Because the first axis, the x-axis, is now our t-axis, and our y-axis, we're now calling our p-axis. And then these 2 points here, I guess we would have at 1 p.m., so when t was 1, then p was 100. When t was 3, then p was 220. So we have 2 points, 1 comma 100, and then another one, 3 comma 220. Now let's just plot those points here. We have at 1, we had 100. And at 3, we had 220. Now, we could say, okay, then, since we were going a constant speed, and that was the thing, right? We had our cruise control. So that means we had our cruise control on in the problem, so that means that our speed was constant, right? So we had a constant speed. And think about this, if you look down at your speedometer when you're driving, speed is in miles per hour, right? And let's look at this. P is in units of miles. So I'm going to put MI for miles there. You don't need to do this in this homework, don't worry. But T is in hours, HR. Now let's stop for a second. Pretend that none of this exists, and all I did was I gave you these 2 points and said, find the line. Okay? What you would do, of course, you'd say, well, I need a line. So I need a y equals mx plus b. Y equals mx plus b. Now you'll notice we're not using x and y, right? We're using p and t. So let's go ahead and change that. Let's say, hold up. The y-axis is now the p-axis. And the x-axis is now the t-axis, so this is what I'm looking for. I'm just changing labels, right? I could have called them smiley face and frowny face, but this kind of makes sense because you have time is t, yeah, okay, and then position is p, yeah, it makes some sense, okay? So this is what I want, meaning I need an m and I need a b. Okay, so I would find my m, I'm going to find my rise and my run. Here my run is a total of 2, because we're going from 1 to 3. And then we're going to rise from here to here, and that's 220 minus 100. Or you could say, what's the distance between 100 and 220? Well, that's 120. Okay, then, my slope would then be my rise over my run, 120 over 2. 120 over 2 should be 60. Now, we don't really need to do this, but we're going to. What are the units of m? Well, let's think about this. 120 watts are we talking about here? Well, if P is, and this is the nice thing about having all this stuff written out, you could say, well, P is miles, right? That's right there. So the difference between the first mile marker and the second mile marker, well, that was a difference of miles. That's the thing that you just measured, right? You measured miles. So I'll make a little bit more room here. What you just did is you took 120 miles and you divided by 2 watts. Are these seconds, sandwiches, smiley faces? No, it's hours, right? There were 2 hours went by here. So you're dividing by 2 hours. And so 120 divided by 2 is 60 watts? Well, miles per hour. And in this case, your slope represents your speed. So I said, if you didn't know, if you just hit the cruise control and you're just going, I never said anything about what speed it was. If you had this information, you could find out what speed you were going. Interesting. Calculus is all about this. If you take calculus with me, this will be the first thing we do on day 1. But anyway. So, okay, we're halfway there, right? We have that P equals 60t plus B. Now we just need to find a B. I could do that by plugging in either of these points. So I'm going to do that now. I'm going to plug in, well, the easy one. How about I plug in a 1 for t, right? It has to be the case that when I plug in a 1 for t, I get out a 100 for p. So when I plug in I'm just doing it right here. I plug in a 1 for t, add b, I get out a 100. So that's the same thing as 100 equals 60 plus b. So b must be 100 minus 60, which should be 40. Right there. Now we have our model. This right here is our model. P equals 60t plus 40. Let's check and make sure that when I plug in a 3, I get out a 220. Okay, so there was all the work. Let's just check it with the other point. When I plug in a 3, so when I have my P equals 60t plus 40, it should be the case that when I plug in a 3, I get out a 220. Oops. So let's see, P equals, plug in my 3, 60 times 3 plus 40. Now, man, okay, 60 times 3. 60 times 3. Oh, that's 6 times 3. That's just 18, and then the 0. So 180. There you go. P equals 180 plus 40. 180, let's count by tens. 180, 190, 200, 210, 220. There you go. Okay, so 180 plus 40 is P equals 220. Nice. There we go. And we could draw our line like this if we wanted. We'll go through here at 40. And since we're in my class, I noticed that this line that I just drew also went through the x-axis. So I'm not done, am I? I need to find out where this goes through the x-axis. Let's see. Okay. I have my model. Here it is. I have the equation of my line, which we're calling my model. And we'll talk more about this in just a second. I want to find out where does it go through the t-axis. That happens when p is equal to 0. So 60t plus 40. bring the 40 over, so that's a minus 40 equals 60t. Divide, I get minus 40 over 60 equals t. That's the same thing as minus 4 over 6 equals t. And then if I have both of those, I have minus 2 over 3 equals t. So that must be that guy, so I'm going to label him minus 2/3. So I guess that means 2/3 of an hour before noon, because t was time after noon. So that means 0 was noon, 1 was 1 o'clock, 2 was 2 o'clock, 3 was 3 o'clock. So then minus 2/3 would be minus 2/3 of an hour, or 40 minutes before noon. So 11:20, something like that. I don't know, I didn't check any of this. If I said something wrong, forgive me. But anyway, now here's our model. Now, let's talk about this. So all of that to get a model. And what use is a model? Well, with this model, we can answer really any question that we want to know. What's nice, one of the things about it, is it tells us the speed. As I said, the slope is the speed when you're graphing time versus miles, right? Or hour, and in particular hours. So we have the slope is rise over run, which is miles over hour, miles per hour. That's nice, but that's more advanced than what we really care about. One of the nice things about this is we could ask the question, where were you at 2 o'clock? Where were you at 2 o'clock? Pause the video and see if you could figure out how to do that. At 2 p.m., where were you in terms of mile markers? What mile marker were you passing at 2 p.m.? Pause the video, figure that out. Okay, so t would, and now remember, this is a relationship between position and time. So if I know position, I could find the time. What we're looking for is when I plug in a 2, what value do I get out for p? And so there I could say, okay, being really explicit here, at 2 p.m., that means that t is equal to 2. So I'm going to plug that into my model, and it's going to tell me 60 times 2 plus 40. 60 times 2 is 120, plus 40 is 120 plus 40 is 160. And so that would mean here at time equals 2, I was at mile marker 160. We could also ask questions about if you were at what time, so think about what we're asking now, at what time did we pass mile marker 300? Okay, so let's think about this. See if you could figure that one out. At what time did we pass mile marker 300? One of the great things about having drawn this stuff out right here is I could say, well, hold up, okay, we want to know what time, so in other words, for what t are we at 300? Well, that means when was my position equal to 300? At what time would at what time would I get to mile 300? So in other words, we're saying when we get to 300, when the output is 300, what would the t be? In other words, plug in a 300 for plug in a 300 for position and solve for the time. So I'm going to write this out. P equals 60t plus 40, and we want to know when P is 300, what time does that occur? Now we're just solving for t. So I'm going to subtract 40 from both sides. That should be 260 equals 60t. Divide both sides by 60. That is 26 over 6 equals t. Right? I'm just dropping the zeros there. And then that's whatever that is. What is that? 13/3? Something like that. A half of 26 is 13. So yeah, 13/3. T equals 13/3. which, I don't know, what is that? 12 would be 4, so 4 hours, 4 and a quarter hours. 4 plus a third, or 4 and a third, 4 and a third hours, so 4 hours and 20 minutes, so 4:20. 4:20, okay, but anyway, that, and again, that doesn't really matter. This would be, as far as I'm concerned, a perfectly good thing, a perfectly good answer right there. Time is 13/3, but that's the idea here. Is now we could describe, this describes a given scenario. But I said that these things are almost never 100% accurate. And what do we mean by that? Well, on one hand, was it exactly 1 p.m. when you looked and saw that you were at mile marker 100? And was mile marker 100 exactly at the front of your car? Or was it maybe a few inches ahead, right? And when you passed mile marker 220, was it exactly the same distance that mile marker 100 was when you passed it? Probably not. Was the time exactly 3 p.m.? Or was it 3 p.m. and 5 milliseconds? Or was it actually a second before 3 p.m.? Or, and you could see, now here's another thing, is there's the big assumption here, that cruise control actually kept you at a constant speed. Does cruise control actually keep you at a constant speed? Well, in theory it does, but a lot of things would have to be true for that. Like, if the highway ever goes up, if you ever go uphill on the highway, you're going to slow down a bit before cruise control speeds you back up, right? So you weren't going 60 this entire time. You were probably going up and down a little bit, so your slope wasn't always 60. You probably slowed down a bit and then came up a bit and then slowed down and then went above. That's just life. No model is ever 100% accurate, almost. Right? So that's what we mean by this, that that we're making a lot of assumptions that don't exactly reflect the real world, right? Another thing we could say, like, were you actually driving like back here at what would have this been, 11:20? Were you? Because this says that you were, and that you were at mile marker 0, right? At minus, when t was minus 2/3, then you were at mile marker 0. The output was 0. That's what the t-intercept is, right? That the p is equal to 0. Were you actually there, or did you start north of Washington, right? Were you actually driving it here? And so this model, if you just go with this blindly, you say, well, this model says that, 9,000 years ago, I was at mile marker -6 billion, whatever it would be, right? Is that true? No, of course not. You weren't driving 6,000 years ago. At some point, this thing breaks down. And I have another example of model breakdown. Let's say you're a biologist and you're studying certain bacteria that you have in a petri dish, and you want to make a mathematical model of this, of the population of bacteria in the petri dish and how it grows. Okay, so we're going to let capital P be the population, that is the number of the bacteria in the petri dish, and we're going to let T be the time in minutes since the time you start your experiment. So we're going to go into the lab, we're going to count the bacteria, we're going to start our clock, okay? Or probably you're going to take a picture of it and have a computer count the bacteria. But you're going to notice when you take the picture, you start your clock, and we're going to call that time equals 0, okay? And here's some data that we have. We have started with 100 bacteria in the petri dish, okay? So that P is equal to 100 when we start our time, when time equals 0. That gives us a point. That T and P, T comma P, so we're putting, again, time on the input axis, and we're putting population P on the output axis. We have a point, 0, 100. So let's go ahead and mark that in. I'm going to put 100 right here. There's 100. Okay, now what you notice as you do this experiment is that the population doubles every so often, and this actually makes a lot of sense, because each of those bacteria themselves separate. They reproduce asexually, so they themselves split into two. So, for instance, if you started with one bacterium, over some time it would split into two. Now you have two bacteria, and then over time each one of those would split into two, and then you would have four. And then over time each one of those would split into two, and you would have 8. And so actually this is a very, very good assumption whenever you're dealing with populations of anything, not just bacteria, but animals. They kind of have the same thing, only it's not necessarily doubling, but there is some time when the population doubles, right? And that's what we're noticing here, is that every minute that we check, after 1 minute, we take a picture, have a computer count the number of bacteria that are in the Petri dish, and we find, it's about 200. Okay, another minute goes by, and now those 200 have doubled, and now we have 400. More time goes by, and we went from 400, it doubles, and now we have 800. And so let's plot these points real quick. So when time was 1, when t was 1, p was 200. So here's 200 right there. Okay. Now, when time was 2, p was 400, so I'm going to take my 2 and go up here to 4, like that. When time was 3, it was 800, so it's double that amount right there. Okay, and yeah, hold up. Ooh, what if this continues? Well, at 4 it would be 1600, and now it's already off of here. 800, 1600 would be up here. I could, well, let's do it. Let's put the dot way up here. It would be up here. Okay, now here's the question. Is this a linear relationship? That is there a line that describes this? Well, no, these points do not lie on a line. They're nowhere near a line. If you tried to draw a line from here to here and think, maybe this line will predict what's going on here, you'd see like, no, it really doesn't. It would do a really terrible job. It might work okay from here to here, but afterwards it's going to get really bad. So what if you draw a line from here to here? Well, maybe from there to there will work. It might do a better job, maybe. Oh no, it's not. It's because this line's going to come this way. It's going to get really bad. Turns out that this relationship is non-linear, and I can show you kind of what's going on here. If we think about the original population, when t was equal to 0, we had 100. Then when t was equal to 1, we took 100 and we multiplied it by 2. In fact, that's exactly how I got these numbers. I just multiplied it by 2. And then when t was equal to 2, we took the previous thing, 100 times 2, whatever that previous population was, and we multiplied it by 2. Right? Now, when t is equal to 3, we took what we had before, which is 100 times 2 times 2, and we multiplied it by 2. And so on and so forth, right? And so this model, if we clean this up a little bit, we have 100 times 2 when it's 1. We have 100 times 2 times 2, which is 2 to the 2, when t is 2. Here we have 100 times 2 times 2 times 2, which is 2 to the 3. And we can see what's going on here, right? The 100 just kind of comes along for the ride. And in fact, if this is 2 to the 0, isn't that the same thing? 2 to the 0 is 1. 1 times 100 is 100. Hey, this actually works really well, right? Whatever the time is, you plug it into the exponent here, and we could say then when t is equal to any time, then what we should have is 100 times 2 to the t. And indeed, yeah, plug in a 4 into this, 100 times 2 to the 4. Let's just try it. When t is equal to 4, we have 100 times 2 to the 4. That's 100 times, we have 4 2's. Right? 100 times 2 to the 4 is the same thing as 100 times 2 times 2 times 2 times 2. 2 times 2 is 4. another 2 times 2 is 4. 4 times 4 is 16. 100 times 4 times 4 is 16. And 16 times 100 is 1600. Yeah, it works. Cool. And so you say, I have a model that works. And so you plug this into Wolfram Alpha, or whatever you do, or Desmos. You say, okay, actually you would do a y and an x, but anyway, you'd plug this in and it would draw your thing, and this is what's called an exponential function, and it would look like this. And it goes up and so on and so forth. But is this really accurate? Well, maybe it's somewhat accurate, but really, like, was it exactly 200 of these things, right? As you hear, we're talking about this line right here. That a model, we have our model, which is population is equal to 100 times 2 to the t. There's your model. And it does a good job of describing what's going on. But in reality, this would probably be 207, and this is probably 410, and this might be 798 or something like this. This might be 1601, and maybe it wasn't exactly 100, maybe it was 102. That's real data, is more like that. You could simplify it and say, yeah, this is close enough. And so it will describe, this is an abstract description of a concrete system, or using mathematical concepts and language. Yeah, it's not 100% accurate, maybe it's good. They usually break down at some point. And this is what I want to say. So let's use our model to predict how many bacteria will we have 4 hours and 20 minutes from now, or 4 hours and 20 minutes from the start of the experiment. So 4 hours and 20 minutes is actually 260 minutes. 260 minutes. I'm sure you could calculate that. So if we wanted to know how many do we expect 260 minutes after the start of the experiment, we would say, well, when t is equal to 260, we plug that into our model. And we get p equals 100 times 2 to the 260. And that is approximately 1.85 times 10 to the 80. Now, so our model predicts that there will be 1.85 times 10 to the 80 bacterial cells, bacteria in my Petri dish. Is this possible? Well, in the universe, there is approximately 1 times 10 to the 80 protons in the observable universe. Each one of these bacteria have millions of protons in them. So is it even possible to fit that many bacteria into a Petri dish? No, absolutely not. That's ridiculous. This would actually, I did the calculations. Each bacterium, and we're talking about like an E. coli bacteria, each bacterium is about 2 to the negative 15 liters. Right, that's the volume of one of those guys. Very, 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 very small number. It's like 0.000002 liters, right? So that many liters. Multiply that by 185 of the bacteria. What would be the total volume of the bacteria? Well, that would be 3.7 times 10 to the 65 liters. 3.7 times 10 to the 65 liters is about 60 times the volume of the Milky Way galaxy. So clearly something broke down, right? Like there's no way that if you notice, hey, we started with 100, hey, we have 200 now, hey, we have 400. There's no reason to think that will continue on indefinitely. At some point, the model breaks down, and really, the bacteria exist on the petri dish and are eating the substrate, the food that's in the petri dish. At some point, there won't be any food left, right? And they're going to get overcrowded and they're going to start to die off. And so what you actually use, if you're going to model population growth, it's a different kind of thing, but you use a type of thing instead of an exponential. It goes like this. It starts off exponential and then it usually decays. And then it's a question as to what happens. Eventually, if they're all there and they've eaten up all their food, they're going to start to die off, right? Or maybe you add more food and maybe it goes up a little bit and whatever, we don't know what's going to happen. But at least in the initial place, an exponential, this model, is a good fit for your data. But you have to know that at some point, you can't expect that to go on forever. The same way with our car that when we were driving earlier. Were you driving 6 years ago? No, well, you haven't been driving for that long. Are you going to be driving like 60 years from now? No. So at some point, this model we have of our trip on the highway, it's got to stop at some point here and some point back here. Otherwise, the model's going to break down. Right, and that's what we mean by that. So these models are just approximations of the real world. They're not 100% accurate, except in a very, very specific circumstances, which we're going to do right now. Number 2 says the temperature of 0 degrees Celsius is the same as 32 degrees Fahrenheit. A temperature of 10 degrees Celsius is the same as 50 degrees Fahrenheit. And it even tells you, use ordered pairs, CF. Okay? So this is what I mean, like, these problems are going to take the guesswork out of this. Obviously, C is going to be, because of this order right here, you know that C is going to be the horizontal axis or the input axis, and F is going to be the vertical axis or the output axis. Okay. Now it tells us to do 2 things. Find a linear equation, that's a linear model, for these points. Second, use the linear equation, or your model, to find the temperature in Fahrenheit when it is 30 degrees Celsius. Now, like I said, some models are accurate. You probably couldn't even really call this thing a model because we're not like measuring temperatures and like seeing, well, do we have a description of what would the temperature be at a certain time, or if you do add this much energy, what would the temperature be? It's not like that. We're just saying like there's 2 ways of measuring temperature, and they're like by definition off by this much. When 0 Celsius is 32 degrees Fahrenheit, that's just what it is. And so when it's 10 degrees Celsius, it is 50 degrees Fahrenheit. That's just the way it is. And so so this isn't so much a model. We probably shouldn't even call this a model. We're just converting between 2 things. So, but anyway, we're going to pretend like that it's a model and go on with this. So, okay, I told you there are 4 things you're going to do with this type of problem, and you had better do what I say. Or I swear sulfur will rain from the heavens. Okay? These are the 4 things. At somewhere on your page, you need to have what you want, and what you want is a linear equation, a linear model. So I want to see that somewhere. Now we'll talk about, do you need to have it be a y and an x, because already you're not calling them y and x. We'll get there in a second. I want you to define your variables, just like I did earlier. Let P equal population, number of bacteria, or let P be position in miles. This is what I mean by that, okay? We'll do that with this one. We'll do all of these. And that's what I expect. 3, graph. You will graph every one of these. Your graph will have intercepts, right? Because it's going to be a line. Every single one of these is going to be a linear model, so you will be drawing a line, and guess what? A line will have intercepts. I want to know what those intercepts are, because in my class, like I've said a bunch of times, every time you graph something, and it goes through the x-axis or the y-axis, or the input axis and the output axis, the c-axis and the f-axis, I want to know where it goes through. So you will label where those intercepts are. You will also label the axes, right? And is this going to be x and y? No, it tells us that it's not x and y, it's c and f. So we're going to have, it's going to look something like that, okay? So that's 3. And finally, give units with your answers when appropriate. We'll get to that in just a second, but you have to do each of these 4 things to receive full credit on this homework. Okay, I want to see every one of these. Now I will say they don't necessarily need to be in this order. One of the reasons why here is because, like I've said before, when I read a problem and it says a rectangular yard, I immediately start doing this before I even know what I want. That's a good habit to be in. Just start writing down. It says rectangular yard, so I go, okay, there's the width, there's the length, the area is width times length, and the perimeter is 2 times the width plus 2 times the length. Okay, I have that. Keep reading and so on and so forth. That's already on your page. That's cool. If that's how you want to do this and you want to start setting this up, cool. You don't have to have what you want first before you start writing down your information. That's fine. But all of these things must be on your paper. Okay, so let's do this the way that I would want it done. So, the temperature at 0 degrees Celsius is 32. At 10 Celsius, it's 50. Okay, find a linear equation for these points. Okay, so we're given 2 points. It tells us to use ordered pairs C and F. So let's go ahead and just define what this is. So we're doing number 2 here. Right? Let C be degrees Celsius. Degrees Celsius. You could just put degrees C. Let F equal degrees Fahrenheit. That's fine. That's fine for this. We know what that is. If you know what that symbol is, that means degrees Fahrenheit. Degrees Celsius. Okay, cool. 2 is done. We've defined our variables. Now, what do we want? We want a linear equation. So I want to see this somewhere. So here's my 1, right? Number 1. You don't have to number these. I'm just saying, like, that's that. We're doing number 1. We want a y equals mx plus b. Now, if you want, you could have just said, well, hold up. I already know that we're dealing with C and F, and that C is playing the role of x, F is playing the role of y. So if you want, you could go ahead and just write that out as F is playing the role of y, and x instead of x, we have a C playing the role of x. Okay? Either way you want to do that, or if you want to do it like this, that's cool too. That's cool too, okay? That's what we want. Now let's get our data down here. And we're going to start by graphing it. And I'm going to say, okay, hold up. The 2 things that we have are not x and y, they're C and F, because we've just named them here. So C is going to go here, and F is going to go here. I want to see that, okay? Now let's use our points. When C is equal to 0, because it even tells you to use ordered pairs. Now if you want to write that out, that's cool. If you want, you don't have to do this, but you could go, okay, that's CF. And we have then 0 for C and 32 for F. We have 10 for C and 50 for F, right there. Don't need to actually write the points out. You could just put, I would just say, well, hold up. When C is 0, F is 32. So here's my first point. Hey, one of our intercepts is already done. That's nice. Now, the other one, when C is 10, then F is 50, so he's higher up. 50. All right, cool. Now, it says find a limit. Oh, yeah, we want a y equals mx plus b or a y equals f equal y. We want an f equals mc plus b. How do we find m? It's the same way we've done every time, right? We run this far over, and our run is 10. Our rise is the difference there, so 32, I guess, 18, right? 50 minus 32 should be 18. It's a positive slope, clearly, so it should be m equals 18 over 10, rise over run. We could reduce that if we wanted to, down to 9 somethings, 9/5. There we go. That looks good. Don't have to reduce it. You could write it as 1.8. Why would you want to work with decimals? I don't know, but you can go ahead and do that if you want. There's 9/5 right there. Okay, so I want this. I'm almost there. I'm going to say, since f equals mc plus b, and we know what m is, I could rewrite that as 9/5 c plus b. Now I just need to find b. So I could use either point to, oh, we know what b is, it's 32. Or, you know, if you didn't know that it was 32, you could plug in a 0 for c. So when c is equal to 0, you get f equals 9/5 times 0 plus b. Oh, but what was the output? F is actually equal to 32 there. So when you plug in a 0, you get out of 32, and you get 32 is equal to b. Or you could have said, well, since f is equal to 9/5 c plus b, when c is 10, then f is 50. And we plug those in. I'm going to plug in my 10 here, plug in my 50 here, and I get 50 is the output when 10 is the input. And I get 50 equals 10 divided by 5 is 2, so that's 9 times 2 plus b. b equals, so 50 equals 9 times 2 is 18 plus b. 50 minus 18 should be 32. Yep, 32 equals b. Either way you want to do it, you got the right thing. Okay, so we're going to say, aha, we have the model that we want. F is equal to 9/5 c plus 32. And I would, if I were you, go ahead and check whichever one of the points you use to get that, use the other point to check it, right? It should be the case that when you plug in a 10, you get out a 50. Because when c is equal to 10, f needs to equal 50. So let's check it. When I plug in a 10 plus 32, does that work? Yeah, we just did this, right? 10 divided by 5 is 2. 9 times 2 plus 32. That's 18 plus 32, which, lo and behold, is carry the 1 gives you a 50. Yes. Okay, we're good. We're good. Now, am I done with part 3? Right? Look at my third thing. Have I actually graphed the thing? I haven't actually graphed the thing yet. Right? Let's graph the thing. We're almost done with our graph. We need to actually do this. And I'm looking and saying, are there any intercept? Oh, there's an intercept right there. Okay. It goes through the c-axis somewhere. Where? Well, it's whenever f is equal to 0. So I'm going to come back to this. My f equals 9/5 c plus 32. And say, when f is equal to 0, c is equal to what? Well, let's find out. Subtract a 32 minus 32 equals 9/5 c. Multiply by 5, divide by 9, negative 32 times 5 over 9 c. And I mean that's good enough. But let's just figure out what it is. 32 times 5 is 10. Carry the 1 and 15, and how about 60? Yep. So negative 160 over 9 equals C. There you go. So that is negative 160 over 9. And maybe that reduces. I don't care if it does. Really don't care. It's labeled. We're good to go. Okay? Now, have we done everything for the graphing part? So let's check. Do I have what I wanted somewhere on my page? Yes, I do. Good. Have I defined my variables? Yes, I did. Look, let C equal this. Let F equal this. Good. Graph. Is my graph good? Let's see. Have I labeled my axes? C and F. Yes. Did I draw the actual thing? Yes. Okay. And now, did I label all of the intercepts? Yes, I have. Okay, I'm good to go. Now we could actually do the problem. I guess the first part was to find this. So there you go. That's the answer to part A. It says find a linear equation for these points, or however it says it. It models these points. Okay, got it. Now it says use the model to find the temperature in Fahrenheit. So in other words, it's asking what is the F when it's 30. Now, real quick here, we could see this is the great thing about having this right here. I could see automatically. Oh, and one thing I didn't do, which I did in my head, I didn't say it out loud. I need to assess and make sure that this is this line. The y-intercept is 32, yes. The slope is positive, right? 9/5 is a positive number, so it should be going up. Hey, that looks good. Okay, I've assessed. That looks nice. Now, finally, we're going to use the model to find the temperature in Fahrenheit. So we want Fahrenheit when C is equal to 30. In other words, now look at my scale. It's going to look horrible, but here's the thing. 30 lives on this side of 10. So that means when I plug in a 30, I should get out an F that's bigger than 50. Right? Just look at that. Plug in a 30. And it tells me F should be bigger than 50. This should make perfect sense to you, right? Like, because if it's 50 degrees Fahrenheit when it's 10 degrees Celsius, crank that up to 30 degrees Celsius, it should be more than 50. But it's nice to have this visual here because it will help keep you honest and you can believe what you're doing here. So let's just do that real quick. F is equal to 9/5 C plus 32. And what we're going to do is plug in a 30. We're plugging in a 30 for C. And let's see what we get. When C is equal to 30, what do we get? Well, I guess 30 divided by 5 is 6, right? 30, make sure of myself here. Is that equal to 6? Is 6 times 5 equal to 30? Yes. So 30 divided by 5, the 9 comes along for the ride. 30 divided by 5 is 6. 9 times 6 is 54. 54 plus 32. And let's see, 32 and 4 is 6. 5 and 3 is 8. 86. Am I done? Do I put a box around 86? What was it? 86 sandwiches? 86 kitty cats? No, it's supposed to be 86 what's? Well, and this is a nice thing about having your stuff right here. This says F equals 86. What is F? Oh man, it's been so long. I forgot. I don't remember what Luckily, I wrote down what it actually is. F is degrees Fahrenheit. So I'm going to write 86 degrees Fahrenheit. And now I've satisfied number 4 here. Give units. This is a unit with your answers. Just like with the first example, the first thing we talked about, which was our trip on I-5, if we said, and I don't think I actually did this, but we said like at 4 hours, where would I be? Well, I would be at, or I know it was 300 and we found it was 4 something, but I could do the same thing. I could say at 4 hours, where will you be? You plug it in and it comes out to like 280. It's like 280 what? Sandwiches, kitty cats? No, 280 miles. That you're at mile marker 280. Same thing here. Is it 86 bacteria? Like in your petri dish? No, it's 86 degrees Fahrenheit, because that's what F means. F is the output. And so you plug in a 30, you get out an 86. What does that stand for? 86 degrees Fahrenheit. So please do what I say, right? I want to see each one of these things on your homework, right? You've identified the thing that you want. That's your linear model. And it's probably a good idea to use the actual variables that it tells you to use here, right? To use those names. That's a good idea. We've defined the variables. I've said let C equal this. Let F equal this. That's on there. Good. The graph is there. You've labeled your intercepts. You've labeled the axes too. This will help you in the future. Finally, we gave units with the answer for the thing that they asked me. If they don't ask you for a thing and all they ask is the model, well then that doesn't really apply, does it? Right? It's just like when they ask you a question, don't just give me a number. I want to know 86 what's. I'm going to assume it's sandwiches unless you tell me otherwise. And 86 sandwiches has nothing to do with this problem, so you won't get any credit for that answer unless you have the units there. Problem 8 says graph the ordered pairs M, C, and in the table they tell you M is miles and C is the cost of a taxi. Then it says draw the line of best fit and find an equation of the line. So as you can see, I've gone ahead over here and I've taken the points MC. So, and look at what I've done. I've graphed it. I put M on the horizontal axis, or the x-axis, the input axis, miles, because it told me to, right? And also, if you think about the dependence of how much a taxi costs you, depends on how far you've gone, right? And that's what this is saying. If you take a taxi for 2 miles, it will cost you $4. If you take a taxi for 3 miles, it'll cost you $5.25. The relationship isn't the other way around. You don't, I mean, I guess you could give the guy, the taxi driver the money and then he takes you the miles. You could do that, right? But usually we think about this as miles is the thing that you could change. You could tell him, hey, let's go 10 miles, and then he will charge you this much. It's not, what varies is how far, like you have the choice of saying how much miles. That's why we're putting that on this axis. Don't worry about that right now. It tells you what to do, so we're just going to do it. Now you notice I used a ruler and I measured this out very, very, very meticulously. You will not be doing that, okay? But like I said, for these problems, problems 7 and 9, you'll be using Wolfram Alpha. But bear with me for a minute because we need to talk about what this means, the line of best fit. Before we do that, let's think back to the population in our Petri dish that we had earlier. And we said that if it started off, the population at time 0 was 100 and it doubled every minute, then this would be a really, really good, it would be exact. After 1 minute, you'd have 200. After 2 minutes, you'd have 400. After 3 minutes, you'd have 800, and we could describe that with this model. Population P equals 100 times 2 raised to the power of t. But in the real world, our population is never going to be exact like that. It's going to be off by a little bit. So at time 0, our actual population was just above 100, right there. At time equals 1, the model says it should be 200, but it's actually above 200 a little bit. The population in the real world is above that curve, above the model, what the model says. At time equals 2, the actual population was 398, which is below what the model predicts. It's close, but it's not quite there. It's actually below. And then finally, when time was equal to 3 minutes, we had that our population was 803, which is actually a little bit above what the model predicts. But really, if this were your data and that were your model, it would be a very good fit for the data. What would be a bad fit is if you tried to draw a line from any two of these points, let's say these two, and you say, here's my model, y equals mx plus b. There's my, or it would be p equals mt plus b for some of that. Well, you can see that's a really bad fit over here. It might do good on those 2 points, and it might do okay in this region, right, in here, but as you go further away, it's really bad, and that would be a bad fit. That's because population growth is not linear. This, however, this system that we're looking at, which is the miles and the cost of a taxi, it actually is pretty linear. But just like data in the real world, it doesn't fall on a perfect line. And as you can see, if I were to use the first 2 points here to draw a line, we would have something like this right there, and that wouldn't be a very good fit over here. That point would be a bit too high, right? If I drew a line going there, it would do a good job here, wouldn't do a very good job with that point. And as you can see, it also wouldn't do a very good job up there. If I use these 2 points here, it might do better, but the idea then is to find the line of best fit. How can we get as close to as many of them as possible? And to really illustrate this, we're going to go to Desmos. So I've graphed 4 points at 1, 1.8, 3, 3.1, 5, 3.9, and 7, 5.3. We're not using the ones from the example in the book because they're so far stretched out. You know, you have like the X values like 2, 3, and 5, and then way over at 10 and 20. It just stretches out too far. So I made this example up. Now, what we're looking for now is a line. We want the equation of a line. In other words, we want a y equals mx plus b. So let's pull that guy up right here. Y equals mx plus b. Now, as you can see, this is y equals 1x plus 1. This does not do a very good job of approximating it. So we could mess with this thing, right? I could bring him down some by bringing b down, and I could see, okay, that's nice. It's still not a very good approximation. Maybe I need to bring the slope down some too. It seems a bit high, right? Another thing to notice is, like, if I were to, I'm going to make him a little less steep there and bring him up. Like, if I try to get through these first 2 points, well, now he's not doing a very good job with the other 2 points. And there's actually a way to quantify this. Right now, and I'm going to bring this back up a little bit. Let's bring him back up to 1, 1, right where we started. Now, don't worry about what I've written here. Like these actual things, these x equals whatever. You don't need to, if you want to, pause it and figure out what I did here. But really, now look at what we have. Each red line gives us the distance from the line that I'm using as my model, from my approximation, to the actual points that we want. And you can see that the bigger these lines are, the farther away it is from the actual, from the points, right? And what I've done here with these D's, you look down here, I have a D1. What I've done is I've said, well, what is the value of the line here when x is equal to 1? Well, it's whatever it is when I plug a 1 in for x. So I have 1 times m plus b. That's the value there. And then what's the distance from that line to the actual point? Well, the actual point's value there is 1.8. So we take the line minus 1.8. Oh, but look, that's a negative number. It's negative 1.44. You can see if I drag this up here now, the line is bigger, or it is above the point. And so when I take the value of the line there which is at m times 1 plus b, and then I subtract 1.8, I come down, and now I have a positive value for my distance. That's going to come into play in just a second. But now, watch this. What I'm trying to do, let's think about this. The line of best fit should have the property that all of these little red lines, which we're going to call the error, E-R-R-O-O-R, right, the error, we want those to be as small as possible. And right now, I'm going to just play with this and just visually try to get it so that these things are small. You see, right now, I'm trying to make all of them small. Now, there's a problem here, though, is if all I do is just add up the distances, D1, D2, D3, just as such, some of them are positive and some of them are negative. I really want to make this point here. I'm going to make the slope really big and come down. And you could see, like, visually, that's not a good approximation. That is not a good fit. That line is not best fit. It is not a good fit for these points. But if you look at some of the distances are negative, these two are negative, these two are positive, D1 is negative, D2 is negative, D3 is positive, and D4 is positive. If we just added those up, which I do right down here, D1 plus D2 plus D3 plus D4, you get something that's pretty close to zero. The idea is we're trying to make all of those distances simultaneously go to zero. But if you let them be positives and negatives, they might just cancel out. And it might actually be a bad approximation. Like, I'm going to really exaggerate it here. Make the slope really big. Drag this guy. I can't make it that big. Drag this guy down a little bit, and let's see. The error obviously is huge, right? And if I zoom out, you can see, like, the D1 is -3. D4 is +3. D2 is -1.2. D3 is +1.2. And when you just add them all together, you get something that's pretty close to zero. So you might think, hey, that's actually a good approximation. Well, that's not what we want. Yes, we want to make the total distances as small as possible, but it's not enough to just add those distances together because, well, some are positive and some are negative. So what we want to do is here, I have E equals error, and that's what I'm just going to call it, the error. The error is then the squared distances all added together. Why? Well, if we were doing a class on this, if we were learning actually about this stuff, like you would learn it in statistics or in a mathematical modeling class, this is called the method of least squares. And the idea is that by playing with this stuff, so now let's look at what happens to E right here, which is now 22.5. It's a measure of the total distance, yes, the squared distance, but now the sign won't matter, and we won't have that problem where when you have a bunch of positives and a bunch of negatives, they cancel out and you get something, look at that, minus 0.9. That's not a very good measure. What we want here is I'm going to bring this slope down some, bring this guy up some, and we'll try to get it. So you can see now the error is a total of 1.5. I think we could do better. Let's bring this guy down some more. I'll bring this guy up some. And I'm just eyeballing this, right? And this is what your book wants you to do, is just kind of eyeball it. Now, I hate that. I don't want to do that because what I notice is, well, okay, we're getting the total error down to like 0.4. Can we do better? Well, let's see. Maybe if I bring this guy down a little bit more, bring this guy up a little bit, and yeah, it's getting a little better. 2.8 or 0.28, all right? Maybe if I bring him down a little bit more. Let's bring him down to like 0.6. Okay, now our error's at 0.3. If I bring it up, look at that. It went down to 0.10. So this isn't a terrible approximation of these points. Maybe we could do better. Let's bring m down a little bit more. We'll make them a little less steep. Maybe 0.56. Bring this up a little bit, and let's see what our error looks like. 0.06. Look at that. 0.06. That's not bad. And so what your book wants you to do is to just like eyeball it and say, yeah, this looks good. I'm getting it. Getting all of the line is as close to as many points as possible. But we're going to do one better here. What we're going to do is there is actually a method that uses this. We want to make all of the squares as small as possible. And what we're going to do is go to Wolfram Alpha. And what we want is a line. We're going to take a bunch of points, and we want a line from it. This is called linear regression. Oops. And what we're going to do is just take each of our points here. See, I already did it here. I guess I already did it. Let's just, I won't type through and do it. So what we do is we just take each one of our points, 1, 1.8, and we plug it in. We go linear regression, 1, 1.8. Actually, let's do it. 1, 1.8. Now I'm going to do a comma, and I'll do the next one, 3, 3.1. So parentheses, 3, 3.1, and parentheses, comma, next point, parentheses, 5, 3.9, 5, 3.9. It bugs me, I'm going to do that. And then parentheses, or comma, parentheses, back, and we got 7, 5.3. 7, 5.3. And let's see what it does. It goes through, and there is a method of making this E back here, right here, as small as possible. And if you take calculus, you will know how to do that. There is a way of taking this E and changing M and B, just like we're doing here, right? You change M and B until you make that E as small as you possibly can. That is called the least squares regression. And here you go. Plot of the least squares fit. And that's what we're telling it to do. Do a linear regression. In other words, find the line of best fit. And it's going to default to using least squares. It's going to take all of those square distances here. The distance from the point to the line. This distance from the point to the line. This distance from the point to the line. This distance from the point to the line. And it's going to mess with that M and the B until they all get as small as possible. And then it is going to give you a model for that right there. And what it tells us is that it's 0.565x, 1.265 for B. I'm sorry, so the M, the slope here, should be 0.565, and the B should be 1.265. So let's put that in here. M needs to be 0.565. Hey, look at that. Hey, and look what I got. 0.56. I was really close. That's nice. Now, let's take a second here and see when the one that I eyeballed, I got 0.066. Let's see what happens when I do this. It's 565. And then the other one was 0.1265. So let's bring it back. 0.1265. And yeah, well, we got a little bit better. That the error turned out to be, instead of 0.066, now it's 0.063.
but it is even better. I think the only reason I was able to get it down that close just by using my eyeballs is because I did this last night and I kind of knew where I was heading. So it's somewhere in the back of my head, I was like, yeah, it's close to 0.56. And I kind of went for it subconsciously. The problem is, like, this could be so difficult to do, and I do not want you guys to do this on Desmos. Like, please don't do this. This is way more than what we're ready for in our class. I just wanted to show you that, because it bugs me when they're like, find the line of best fit, and you're sitting there going, gee, I don't, is this good? Maybe I'll just kind of, maybe like this. And what you're doing is, you're doing it with like a pencil and paper. And did you actually draw them very well? And once you finally get it, they want you to like find the equation of the line. Well, now you got to find 2 points on the line and find the slope and then try to find the intercept. And like, did you find the points very well? It's all just a guessing game when there's actually a way of doing it. And it's called linear regression, and it will find it. You could prove that this is the best line for this. This minimizes all of these little distances right there. Okay, so this is what I want you to do for these problems, is just go to Wolfram Alpha. So let's take the example that we were doing in class. We had a bunch of points that you already plotted, right? Hopefully. If not, I may have said that in the next part. I went ahead and recorded everything else I was going to say. Forget what I've said and what I haven't. But we have our points. They were for the taxi ride and the miles. The miles traveled was 2 and the cost was 4. So let's do that. 2, 4. Now, the next one was when you travel 3 miles, it costs you $5.25. $5.25. Okay. Now, next point. It says that when you travel 5 miles, it costs you $8.50. So 8.5. It says that when you travel 10 miles, it costs you $16.25. $16.25. Finally, when you travel 20 miles, it costs you $31. Now, so we're going to say, okay, instead of plotting those points, trying to find a line, I'll do this and I'll do that, and then, that's good enough, and then try to find the equation of that line, let's use calculus to actually find the minimal distance between the line and each of these points. I'm going to minimize this total distance. And it does. And it says that the line that minimizes each of these distances from the line to the point, right? You have a distance here, that would be D1, a distance here, D2, distance here, D3, distance here, D4, distance here, D5. We're going to minimize that. We want to make those as small as possible, and the line which does that is 1.50803x plus 0.93578. Now, there's another thing I want to say here. You'll notice this r squared right here. This is a measure of how good of a fit it is. And the closer this value is to 1, the better of a fit it is. So if you took 2 points that are on the same line and did a linear regression with that, let's do that real quick. Linear regression. And let's take the point 1, 1 and 2, 2. They should be on the line y equals 1x plus 0. And yep, there it goes. The linear best squares fit is just y equals 1x plus 0. Let me drive that point home. Let's make this a 2 and a 3. The slope should be 1, and it should go through at 1, so it should be x plus 1. There you go. So the least squares best fit is x plus 1. And look at r squared is equal to 1 because it's exact. There's no error. The total distance is 0, right? And so that means it's a perfect fit, so r squared is equal to 1. Anyway, back to what we have. You can see it's a pretty good fit, 0.9997. That means it is actually really good. It's almost linear. So anyway, what I want you to do is for these problems, you will graph it, and I will explain more in just a second of what I'm looking for on your page. But you go in, you put you type into Wolfram Alpha linear regression. Put each of your points in. Make sure you've separated them with commas here, right? The input value, comma, output value in parentheses, comma, parentheses, input value, comma, output value in parentheses, comma. You need commas between these guys. And it will do this for you. It will find the line of best fit. It will do a linear regression. It will find the line of best fit for your data. And what you do is you're going to take that and write it down, and I will explain the rest.
So then what I want to see on your paper from Wolfram Alpha is the actual model that it gives you, the linear regression that it gives you, right? This thing. And it's going to give it as y equals this x plus this. But another thing I want, please do this, is define your variables for this. Okay, so define your variables, right? And that's given right here, and it even tells you which one is the input, which one's the output, right? So define your variables, and here we're letting m equal the length of a taxi ride in miles. It has the units. It's not just, don't just put m equals miles. Like that's lazy. Like think about the context of this. There's a cost of a taxi, so miles, what is it? Miles like that you ran this morning when you did your morning jog? No, it's the length of the ride, right? Like obviously that's what this table is telling you. C is the cost of the taxi ride, and that's right there, okay? So that's easy enough. Please, so what I want you to do is you've gone to Wolfram Alpha, you've plugged in those points, and it gave you this. It also gave you a graph, right? Just copy that graph. You don't need, please don't measure this stuff out. Just look at the graph that Wolfram Alpha gives you and make it look like that, just generally. It's fine, like don't go nuts with it. Right? But I do want to see intercepts. And you might say, in this context, intercepts don't make any sense. And you'd be absolutely right. Because what would the y-intercept be? Well, that would be the cost of the taxi when you've gone 0 miles. When miles is equal to 0, the cost of the taxi is 0.93. 0.93. You have, if you haven't gone anywhere in the taxi, you have to give the guy 94 cents. That doesn't make any sense. You're right, it doesn't make any sense. And what about over here? The m-intercept says that if you've gone negative 0.6 miles, the cost is 0. So he'll take you backwards, a half mile backwards for free. No, obviously not. The model breaks down. There is no 0 here. Then why do I want you to do this? Because I want you to get in the habit of every time you draw something to label wherever it goes through an axis. That's 1. 2, this is really good exercise. Like you should be able to do this. And look at how I did this, right? How did I find the y-intercept? That's the y-intercept. You could also get it by plugging in m into here. I mean, plugging in 0 for m. Yeah, okay. And then how did I get the m-intercept, the input intercept? Well, I set the output equal to 0. I did this, then I did this. Then I plugged this into a calculator and got this. You don't need to actually plug it into a calculator. I don't care. If you want to leave it like that, that's good. It's just really good exercise in this case. Like, you're absolutely right if you were saying those don't make any sense. Why would you do them in the first place? You usually wouldn't, okay? It's that I want you to be so familiar with finding intercepts that any chance we get, I want you to compute them. Okay. So that's it. For these problems, number 7 and 9, it's probably best to go ahead and draw your axes first and label the points, right? Put all your points on the axes. Define your variables, then go to Wolfram Alpha, plug in each of the points, say linear regression, and then each of those points, just like we did. Get your model, write your model down, draw the line that you see, or, and you can just eyeball this, right? And then label the intercepts, and we'll call it good. I hope you enjoyed today's class. Sorry I couldn't be there. I hope to see you guys Thursday.